Martin is Thomas Frank Professor of Physics at MIT. He works with ultra-cold atoms, configures them into very interesting arrangements of fermions, which is an undertaking worth doing in the physics world, and has lots of sort of control over atoms at a very low level of say 400 atoms at a time. It's really quite remarkable. And Martin was educated originally in Germany. He came to MIT and did his PhD with Wolfgang Ketterle, and then he postdoced, I think, again in Germany, but anyway, in Europe, and then came back to MIT in 2007, where he now leads a group doing extremely interesting work with small groups of low temperature atoms that can be put into configurations that really produce results analogous to much more complicated systems. I mean, it's an extremely valuable tool. He's also got a lot of enthusiasm for physics, and it gets very high ratings by his students for his teaching. And so with that, I think I will just stop singing his praises, lots of prizes that I'm not going to tell you about, and turn it over to Martin. Thank you, Martin.
So this is actually a perfect introduction to the talk, because it will essentially be about the communication of two quantum particles. And it's therefore very, very similar to the issues that we are facing here in the sound audio. That is at the core of entanglement. So let's see whether I can walk you through. I was tasked with basically explaining why, if I can, the Nobel Prize of 2022 was given to Clauser, Aspe, and Zeilinger, and so I'll try to walk you through the story, and in the end, of course, the goal of this is to end up with the stuff I do in my lab, because then I can tell you about my stuff. But so that will be interesting, whether I get from the beginnings of quantum mechanics all the way to what we do in the lab. If I go, I don't know, too fast or too slow or too crazy, just let me know how things are going. I'll start with Galileo's clock. This is a beautiful drawing, which is probably due to his student Vincenzo Viviani, who so the story is that Galileo conceived the clock, talked to his son about it. Apparently, I'm not an expert on Galileo history, but he didn't build it. His son tried to build it, but then also died. So in the end, it was eventually built by Viviani, and but became not a useful pendulum clock. But the principle is beautiful. And from one of Dan's students, I think, students or postdocs, Dan Kleppner can correct me, Michael Littman, I got these drawings in 3D printer format. So now you can actually print out this Galileo clock and have it play for you. Clearly this, I can show you the video later. I didn't want to try putting a video in here, but like you can print this out yourself these days. 3D printers are not more expensive these days than 2D printers. and then you have your own Galileo clock in your room. I think it's a lot of fun. So that swings back and forth. And the moment we know at one moment in time the position and the velocity of the pendulum bob, we know it for all time, according to classical physics. So that's very powerful. Great. I measure where the pendulum bob is. I measure how fast it is. And then I will know the entire future in principle. And in principle, I could do this with all the planets and know the entire future of the universe. There's this very intriguing subject of chaos already in classical physics that I don't want to get into, which is simply the problem. If you don't make perfect measurements, suddenly we can no longer predict the future. But that is in classical physics only a problem in principle. Like we could imagine knowing everything. There could be some Maxwell's demon that knows all the positions and velocities of particles everywhere, and then we would know the entire future of the universe in principle. So okay, so that thought has to be somehow shattered in this talk. And let's go to the beginning of the 20th century. If you want to read all about the history of atomic physics, you can find it in Dan's review of modern physics from 20 years ago, which will be, Dan teaches you not to use the word very in your writings because it's usually superfluous. That's why I put on purpose very in the title of this slide to tickle him. I hope this worked. What is known at the beginning of the 20th century? Atoms exist. So the idea that atoms are a thing exists. We have Mendeleev, we have spectral lines of elements. So we see there's some sort of quantization going on in nature. We find electrons, ions, and we realize that radiation is created by matter itself through oscillations of charged particles. Newtonian mechanics is absolutely there. Electromagnetism is well established. Thermodynamics and statistical mechanics are there, very well developed, but there is a missing piece. And it's so beautiful to read Max Planck's book on thermodynamics from 1899, which is just before he actually came up with the idea of quantum units of energy. He lays out statistical mechanics perfectly. Everything is in there. Entropy is discussed beautifully. It is just very interesting. He knows he needs to count the number of possibilities that a system has. So the number we would say of quantum states in modern language, he just doesn't know what unit to count them in. And a year later, that unit will be his constant, Planck's constant that he introduces. So everything is sort of almost ready, but there are lots of gaps in understanding. The heat capacities of gases, when you cool down a gas, why do you suddenly see the heat capacity drop to a new sort of level and then flatten out? We know now, of course, this is because of the freezing of the degrees of freedom of your gas. But when you have no idea about quantum energy levels, this is completely obscure. Atoms are, of course, not really understood at the time, and spectral data from the sun, Planck's, what we now know as Planck's radiation law, the spectrum from the sun was completely not understood. A couple of revolutions, radioactivity was discovered, X-rays, electrons, and a realization that statistical mechanics is not, as we know it in 1899, is not able to describe a thermal radiation field. And then, of course, come the revolutions of relativity by Einstein eventually, and quantum mechanics, which I will get into. So here is Planck's spectrum. The classical theory, when you look at the sun, you get this beautiful spectrum, which peaked around the greenish yellow. That's why our eyes work really well there. And it drops off to both sides. So both to long wavelength and short wavelength, we get less spectral radiance. Classical theory is absolutely not able to explain this. You get this black line here, which goes through the roof. And Planck figured out how to heal this problem, but he needed to assume, crucially, that energy is only emitted and absorbed in chunks, quanta of energy, which are related to the frequency of the light, f, by his constant that he had to introduce, h times f. So that was the beginning of the idea of quantum mechanics being necessary to describe the world. There are other signs in the Fraunhofer lines. Fraunhofer looked at the spectrum from the sun and saw peculiar dark lines in the spectrum, sort of missing lines in the spectrum from the sun when he dispersed it using a prism. For example, very famous are the sodium lines here at 589 nanometers. I love them because we use sodium in our lab and use lasers that are at 589 nanometers to cool atoms down to near absolute zero. But what is this? What are those dark lines? That doesn't make any sense. These days, now 100 years later, we know, of course, this is from absorption of atoms in the atmosphere. And every atom has its own fingerprint. So people saw, like, if you look at the spectrum from, if you hold the gas of hydrogen in between you and the sun, you will see absorption lines, and you can also see emission lines. And they're very discrete. And of course, there's no understanding from classical physics why that should be. If you have an idea of the atom being a happy electron running around a proton, positively charged nucleus, that's already a revolutionary idea, but it is still looking like a classical Newtonian gravitational model, if you want. And it doesn't tell you at all that the electron should be on particular orbits. So that was peculiar. Here's a picture of the sodium doublet. Even weirder is when you switch on a magnetic field. These lines split even further, and they split in ways that you cannot explain by simply assuming these atoms have just a usual, typical orbits that we would know and love from a classical particle. So for the experts, these lines, when you switch on a magnetic field and see the lines split in a magnetic field, they already tell you the fact that the sodium atom has a property called spin that will come up in a second. That is an elementary ingredients of particles. More to that in a second. So there were all these riddles, and then Bohr comes along and just ad hoc says, okay, so Planck tells me that energy is emitted and absorbed in chunks, or he needs to quantize the energy of light. Well, then let's assume that atoms only now allow discrete jumps of energy of the electron between different energy levels, and light is emitted and absorbed as the atom jumps from one level to the next, emitting therefore then an integer number of these quanta, which would be very good to reconcile everything with Planck. And he does this ad hoc assumption, calculates the energies that you would that you would find. One slide back, please. Yes. And I just put this equation here. To some, it will be extremely familiar. To some, it will be just a bunch of letters. But it's maybe the point is that you can write down suddenly a formula for energy levels in an atom. And the one thing I can put your attention to is this n here in the denominator. That's an integer. So the energy levels are related to some, square of some inverse integer. And if you put in the various integers and calculate the energy difference between these energy levels, you get precisely the hydrogen lines out. And you can now suddenly explain this weird succession of spectral lines in hydrogen.
And why is it negative?
It's bound energy. So the electron is bound to the proton, and that's why it's negative. Zero of energy is chosen to be the electron being infinitely far away from the proton. So this is great. We have suddenly a description, not an understanding, but a description of these energy levels from hydrogen using numbers that, m is the mass of the electron, e is the charge of the electron. These were known before. And h bar is Planck's constant divided by 2 pi. And you plug it in and it actually reproduces these energy levels. So this combination of constants was previously just measured to be some number, but no one knew where it came from. And Bohr plugs in his idea and gets that number. That is absolutely a revolution and just unbelievable. So clearly there must be some truth in this, but why? It doesn't make any sense, because the electron will fall down usually. It should fall down onto the proton. It's an oscillating charge in this model. It should therefore radiate energy, and the Bohr atom should collapse, and we should all be mushed into nothingness. So clearly we're not done yet. There's an essential ingredient missing: understanding why this should even work. And the way out is Heisenberg uncertainty. And here's the thing, I'll just state it. And let's see where that gets us. Turns out, if I know exactly where a particle is, I actually have absolutely no idea how fast it is moving. If I know exactly how fast the particle is, I have absolutely no idea where it is. To give you maybe an idea of feeling for these words, the top picture here of this particle at a very particular position, that could be just a sudden picture that you took on your camera. But of course, that means, okay, great, you have a beautiful picture of the atom, but you don't know where it is. If you instead use a streak camera, like you expose for a certain amount of time and you see a smear out of the atom over a certain length, then you know quite well how fast that atom was, because you know the time that you took to take this streak picture. But of course, you have no idea where within the smear the atom is. So this is to give you sort of a little bit of a classical analogy of this uncertainty. It turns out it's a problem of principle. Like, if I am trying to measure the position of a particle better and better by confining it with slits and shooting photons at it to reveal itself, I will actually, through that very process, make its velocity more and more uncertain. So you're actually perturbing the atom as you're starting to stare at it. And for people working with optics, this is familiar. If you take a plane wave and you shine it onto a thin slit, the plane wave had a beautiful direction, beautiful, we would say, momentum. But then after the slit, you see there's a diffraction pattern. So suddenly you have directions of light in totally different directions from the original direction of your plane wave. So by confining the light, trying to measure, if you want, where it is, you actually already have perturbed its momentum. So it's a duality that's very well familiar with wave optics. Now, how does the hydrogen atom deal with that, or the quantum pendulum that I'm about to introduce? It actually does a beautiful compromise between position and velocity uncertainty. If I know its position too well, say it's too close to the nucleus, that will make its velocity uncertainty tremendous and will cost a tremendous amount of kinetic energy. So that's not good. If it's extremely fluffy, not at all localized, far away from the nucleus, well, that is not profiting from the attraction by the nucleus. So that's also not good. So the hydrogen atom just does a beautiful compromise between these two limits. And on the lower right, I just show what we pictured the electron cloud looking like around the nucleus. You don't know where the electron is around the nucleus. You only know the probability with which it is at a certain distance, and that is described by this blob that I'm showing here. So this is the way out, and it's beautiful to read Heisenberg's first paper where he actually figures out modern quantum mechanics. He actually doesn't discuss the hydrogen atom. He discusses a simpler system, and it's the pendulum. So like for Galileo, the pendulum was very intriguing for Heisenberg, and actually was the simplest problem he could wrap his mind around to try to understand how quantum mechanics will modify the situation. And he figures out that indeed we cannot speak of, you know, the exact position of the pendulum, because that would make the pendulum's velocity completely uncertain, and vice versa. In the ground state, instead, we have just a probability distribution of where we might find the pendulum. So my mouse pointer, I'm not sure you see it, is now at the lowest state. This is a graph of energy versus position. So low is good, it's close to the ground state. Classically speaking, you would find a point at the bottom of this parabola. That parabola describes the potential energy of this pendulum. But quantum mechanically, that's not possible. That would localize this particle. That would cost an infinite amount of kinetic energy. So instead, it spreads out over the smear that I'm indicating here with various copies of the pendulum ball, the pendulum bob, spread out over a certain probability region. That's the ground state. Let's call that 0. We like this notation where we put this number, this label, into this weird kind of succession of brackets. We call that a ket, which is the partner thing of a bracket. Don't worry about it. This is a very typical way of just denoting a quantum mechanical state. This is the ground state. The first excited state, the one thing I know with certainty is where the atom is not, namely in the center. At the center, I have absolutely 0 probability to find the atom, and it's somewhere else. Why is it not in the center? Well, all that, you know, that gets us maybe too far. But you see, it's very intriguing. Heisenberg figures out that you cannot have any energy of a quantum pendulum. It comes in energy steps. And the higher and higher excited, the more complicated these probability wave functions look. But that is the quantum nature of a pendulum. I just cannot know exactly where it is and how fast it is at the same time. So now, if you don't believe me, there are, of course, a gazillion beautiful experiments demonstrating this wave-like nature of particles and this duality between waves and particles. And one beautiful example, for example, is this electron microscope experiment, where you have 2 ways of the electrons to go, left or right. And if we are serious in describing these electrons like a wave, as de Broglie told us, we should think about them being able to go both ways. Down there, I have a detector. Well, that detector is actually making a position measurement. So it's really asking, where is the electron? And if you just shoot 3, 4, 5, 6 electrons on your screen, you get these little dots. I'm not sure you can see them on your screen, little dots in figure A of this right-hand graph, seemingly random locations where the electrons showed up. But you repeat the experiment over and over again, you get more instances, more electrons hitting your detector. You repeat it more and more, still seems very random, but now you repeat it many, many times and you realize, wow, there is actually a pattern to the distribution of the electrons, a probability pattern, which looks just like the diffraction pattern of a wave from a double slit. So yes, electrons are particles, but they propagate as waves. That's quite a beautiful depiction, and like those we have made. Now, I'm gonna throw everything at you in this talk that you need to know about quantum mechanics, and it's gonna be a lot. There's one more deep thing that I cannot do without, and that's the idea of spin. The intrinsic spin of particles. So you would think, if you have a spinning top, That spinning top can point in any direction. It can rotate about any axis. It should be completely homogeneous across all possible angles that my spinning top can point. Turns out, if you measure the orientation of your particles, they are also in a classical picture, they are spinning about their own axis, like the Earth. So I'm employing a classical picture, which will fail quantitatively, but to give you a picture, each of these elementary particles has their own spin. And you might think, fine, they might have their spin, but that spin should be able to point in any direction. Well, let's measure it. That was the famous Stern-Gerlach experiment. They sent a bunch of atoms, which basically had one electron that was doing most of the job, through a region of a magnetic field gradient. Wow. Okay, so what does a magnetic field gradient do to spinning charges? Spinning charges, they're like a magnetic needle. The direction of the spin and the needle are aligned, and so by throwing this magnetic needle through a magnetic field gradient, I will deflect the needle. And if all orientations of that magnetic needle are allowed, I should just see a boring homogeneous blob at the end of my experiment. Here on the detector, again, where we ask the atoms to show themselves. But instead, Stern-Gerlach found only two discrete blobs, two discrete positions on the screen where the atoms showed up. So that was the demonstration that magnetic moments, like these magnetic needles, they're quantized. The possibility of pointing in any direction is in any experiment not realized. In any experiment, you need to find, for this electron, for example, two outcomes. Either it's aligned with the magnetic field or it's anti-aligned with the magnetic field. Those are the two outcomes. There's nothing in between. If that comes as a shock to you, it's fine. It's like it was a tremendous shock to the physics community. It doesn't make sense. Like, how should directions in space be quantized? But that was what the experiment taught us, and that is the property of the quantum mechanical spin. So it's actually, if we accept it for 1 second, we can say, okay, that's interesting. We have a property of particles called spin now, and I can label the state of a particle by whether it's pointing up or down in such a Stern-Gerlach magnet. Even worse though, leap of faith, before the measurement, I don't know which way the electrons are spinning. Any state before could be possible. Any arbitrary superposition, as one says, like any arbitrary combination of these two outcomes are possible. So we write this in physics as a little equation of, like, I have some admixture, let's call it alpha, of the spin up nature, and I have some admixture beta of the spin down nature. And it turns out alpha and beta are complex numbers, but that's maybe a detail. This is nothing but the qubit everyone talks about. In quantum mechanics, you have the ability to not just think about one state or another, but you can actually make arbitrary, we say, superpositions of these states. You can also think about Schrödinger's cat being dead and alive as a very dramatic example of such a superposition, which is extremely fragile. I think the moment some little atom hits the cat probably has to decide whether it's dead or alive. That is the qubit. And only in the experiment, Stern-Gerlach, for example, we force the state of the system to collapse and reveal, am I spin up? Am I spin down? And this will occur with probabilities given by these prefactors, in fact, the square of this alpha and the square of the beta. So this is maybe the most quantum thing we have in quantum mechanics, just two states up and down. Before I talked about position and momentum, and they already have weird complementary properties. If I measure one, I don't know the other. Here it's boiled down to just two possibilities. I can be up, I can be down. I cannot be both at the same time. So if you want to now go ahead and see like what this came to in the last 100 of years, you can maybe have fun and count it by the number of Nobel Prizes. Should not be the only indicator of progress, but it's a beautiful story how, of course, over the 100 years, amazing progress was made to control more and more light, control more and more atoms, the internal degrees of freedom of atoms, and eventually also external degrees of the atoms, making one big quantum mechanical wave function of many, many atoms sharing one and the same system, having many light particles, photons, share one and the same wave function. So one is the laser that we all know and love, and the other is a Bose-Einstein condensate that I might or might not be able to talk about later. So there were a couple of recent Nobel Prizes in making, manipulating, and measuring states of atoms and photons that were in these peculiar quantum superposition states by Zwierlein and Arosh. And the last year's Nobel Prize was to demonstrate entanglement with photons and demonstrating that quantum mechanics makes particles much more correlated than you could ever make them correlated through classical physics. That I will discuss more in the future. So I think at this point I'm now diving into quantum entanglement, and so maybe I should stop here for a second. What I discussed previously was what happens to a single particle, either a spin, we have spin up and spin down, or a single electron being somewhere or not being somewhere, having momentum and position. For entanglement, we need two particles. So it's one step worse, if you want, in complexity. And that's why maybe I should just wait for if someone has a question.
So you see Jerry Slate's question?
I see a question. Yes, is the electron directionality seen in the Stern-Gerlach experiment the same at the North Pole and the equator? You mean of the Earth? Then the answer is yes. If you bring your Stern-Gerlach magnet, the experiment, to the North Pole or to the equator, you could perform the same experiment. So it has nothing to do with the Earth's magnetic field, which is to a very good degree where you do your experiment homogeneous and will not deflect the electron. But your inhomogeneous magnetic fields created by these two magnets, they will of course create a magnetic field gradient, and that will pull your electron up or down dependent on its magnetic moment.
One question about spin. Are electrons actually, the spin of electrons, aligned, or does it become aligned because we're testing it?
Right. So before the measurement, we don't know the state of the electron. So it's in this most arbitrary state here, which is like, I don't know, is it up, is it down? I don't know. It's the superposition state. But then in the experiment, we're designing the experiment to reveal its magnetic moment to us by throwing it into this inhomogeneous magnetic field and having a detector at the end. So it has to show itself. Which magnetic moment do you have? And indeed, then you only find two outcomes. So it is the decision of the experimenter which way to align this magnetic field that the experimenter brings to the lab that will decide on which axis the magnetic moments will be polarized after the experiment. So exactly right.
I have a question, follow-up question. If you don't have a magnetic field, but you have two electrons floating in space, are they, I mean, this goes correlation, are they correlated in such a way that if you could measure arbitrarily, one would be up, or one would be in one direction and the other one would be in the opposite direction?
This is such a beautiful question. Thank you so much. That's exactly what quantum entanglement will answer. So if I produce an entangled state of these two electrons, then it will be like you say, if I make a measurement of one electron, I immediately instantaneously know what the state of the other electron will be. That's precisely quantum entanglement, and that's precisely the next part of the talk. So that's a wonderful lead in to quantum entanglement.
Thank you.
So this is quantum entanglement. What is it? It's correlations between quantum systems, so plural. Now we talk about at least two, for example, two electrons, two atoms, two molecules, two photons, that are much stronger than any classical correlation could ever be. It's trying to put it in the most dramatic form. We will now go back to 1935, because Einstein was very much like in the same position as maybe now some of you who hear about this talk about position and momentum not being measurable at the same time. That sounded so strange that Einstein, Podolsky, and Rosen went out and actually used quantum mechanics to seemingly prove that quantum mechanics is incomplete. So it's beautiful, right? To try to use the weapons of the enemy to actually turn it against the enemy. And what they were really worried about is precisely what is then reality if we no longer say that the particle has a particular position, it has a particular momentum. It feels eerie to think that sort of it depends on the measurement of what reality is. So they didn't like that at all. And it's precisely what we said for a particle in a certain momentum state, momentum, or the oomph, the velocity is certain, position is completely uncertain. So position has in that experiment no physical reality, they say. And that's very, very uncomfortable. And they design a thought experiment, a Gedanken experiment, to sort of prove that quantum mechanics cannot be the complete story. And they take, and that's really the intellectual advance of that paper, which is beautiful, they take two particles. And let's say they have interacted for some time so that they know about each other. They have, if you want, measured each other, right? And in their example, let's say we happen to prepare these two atoms with a perfectly known separation. So x1 and x2. I know the distance, fine. Now, let me now decide to make a measurement of the first particle. Let's measure the velocity. Ooh, okay. Well, I can do that. I can measure the velocity of the first particle. Of course, I will wipe out clearly any knowledge about the position of the first particle. Fine. That's not so much the point. The point is, the moment I measure the velocity of the first one, I absolutely know with certainty the momentum of the second one. Because I know they started together at a beautiful particular distance from each other, center of mass 0. So if I find the first particle after the measurement moved to the right, well, the second one must have moved to the left with exactly equal and opposite momentum. So interesting. I perform a measurement on particle 1 and I learn instantaneously about particle 2. That's crazy. And by the way, the word instantaneous makes Einstein especially unhappy because of relativity. Information shouldn't travel faster than the speed of light. So if you say something happens instantaneously, that's already eerie. But even worse, I can now decide to measure the position of the first particle instead of the momentum. And suddenly I learned something about the position of the second particle. I actually know that it's a distance away from the first particle as I had it before. So it shows I can measure purely on the first particle and learn everything I want about the second particle, position and momentum. And if in your mind you separate these particles far away, I make a local measurement of particle 1, of position and momentum. I learn something about position and momentum of particle 2, precise information. So that violates the idea that I cannot possibly know position and velocity of that second particle. So apparently there's a contradiction. This, of course, they themselves said, okay, so there is a little catch. There's maybe an objection to this conclusion. And that is that, maybe if someone insisted that I can only discuss two physical quantities as real, if I can measure them simultaneously, well, then maybe that is a different way of defining reality. And then they say like, oh, on this point of view, since either one or the other, but not both simultaneously of the momentum and the position can be predicted, they're not simultaneously real. So this makes the reality of momentum and position depend on the process of measurement carried out on this first system in your mind, far, far away from the second system, which does not disturb the second system in any way. No reasonable definition of reality could be expected to permit this. So it's beautiful. They're offended by this idea that you couldn't assign a reality to both position and momentum. And the catch here is the little which sentence here, which does not disturb the second system in any way. Turns out it's not true. So Niels Bohr was very much tickled by that paper and wrote a paper with the same title. Can quantum mechanical description of physical reality be considered complete? And he said, well, if you change your criterion for what you call physical reality to what you can possibly ever only measure in an experiment, then everything is fine and there's absolutely no contradiction. Which is why physicists have been using quantum mechanics ever since 1925 with success for a gazillion things, and every time got the right answer. And there was, for practitioners of the theory, almost no issue. So it depends a little bit on what the point of view is. So it seems. After this paper, you would say, okay, so it's a little bit about what's your definition of reality, and it's a philosophical matter. Fast forward to 1964. Bell's inequalities. It's actually an amazing paper, very short, where he says like, okay, let me take the idea seriously that what Einstein would like, that really there is a classical theory where in principle I can know position of momentum of my particles. And that classical theory should better be a local theory, because Einstein could not possibly accept that whatever I do on particle 1 should affect particle 2 far away. He takes that idea of this local probabilistic theory and demonstrates that quantum mechanics will be in disagreement with the predictions of that local probabilistic theory. He boils it down to an inequality, a mathematical inequality between measurement results done in quantum mechanics and measurement results obtained from a classical theory. And if you measure in your lab that this inequality is violated, you know this local probabilistic theory is down the drain, cannot be true. So it's no longer a philosophical thing. It's no longer, oh yeah, it depends on your point of view, what you're comfortable with to accept as reality. No, it's now a testable thing. I can test whether the idea of a local probabilistic theory is right or wrong. So that's an amazing thing. I thought for a second whether I should derive the equation for you, and I completely gave up. I'm not going to derive the equation for you. All you have to know is that you can derive an inequality between the assumption of a local classical probabilistic theory and quantum mechanical predictions. And let me take an example of what actually happens, precisely what you just asked. Take two particles, for example, atoms. And what I will do is I will prepare them in a state of zero magnetic moment. So zero total spin. Okay, that means if one is up, the other has to be down, and vice versa. I have to write this in this peculiar fashion here, up for the first particle, down of the second particle, minus down of the first particle, and up of the second particle, because I don't know which atom is up, which atom is down. They're completely indistinguishable. For example, two electrons are completely indistinguishable. So I don't know which one is up, which one is down. So I should not write up one, down two. I have to also allow for the opposite possibility. And don't quiz me on the minus sign. That's if you want the convention. And now what I do, I move them apart by a large distance to really get into friction with Einstein's idea. I move them apart by a large distance, and now I measure the spin orientation of the first particle using my Stern-Gerlach magnets. And it turns out, if I find the first particle in state up, I immediately know that the second particle far away there is in state down. And that's true. And that's exactly what Einstein didn't like. That's the spooky action at a distance. And it's because I knew originally something about the system. I knew that it had zero total spin. So I correlated the two atoms. They were no longer doing their own thing, independent from one another, but they were correlated with each other. Then I took one, moved it to the left far away, one to the right far away, and decided to measure on the first one. And whatever I find, if it happens to point up, I know the second one must be down, and I know it instantaneously. Now, of course, that doesn't violate relativity or anything, because I cannot communicate that beautiful, newly found information to people far away where the second particle is at faster than the speed of light. So I'm not violating any information theory here. But it is still spooky that a measurement should sort of on one particle should do something about the state of the second particle. But you can test whether that is how nature works, or whether it's rather that there are some sort of hidden bells and whistles that make everything classical. So I can just say that first Bell's paper was not like, I mean, it was not like suddenly a revolution in physics. It was not sort of, I guess, discussed too much. It was only slowly that a change of mind took place, precisely by works by John Clauser and colleagues proposing an experiment what one could do. And one way to see that the community changed its mind a little bit is that Feynman in 1965 writes in his lecture notes that this point of this spooky action at a distance was never accepted by Einstein. Became known as this Einstein-Podolsky-Rosen paradox. But when the situation is described as we have done it here in his textbook, there doesn't seem to be any paradox at all. So in 1965, Feynman is like, yeah, that's like, just change your point of view, come over to the quantum side of things, and then you won't have a problem. After 20 years, after Bell's inequalities and measurements demonstrating Bell's inequalities, he writes something different. He writes, I have entertained myself always by squeezing the difficulty of quantum mechanics into a smaller and smaller place, so as to get more and more worried about this particular item, spooky action at a distance item. It seems to be almost ridiculous that you can squeeze it to a numerical question that one thing is bigger than another. But there you are, it is bigger. So this was under the influence of the experiments that have been done in the meantime. So I will now describe those experiments that have demonstrated that quantum mechanics gives the right description and a local classical theory is down the drain. That gave rise to the Nobel Prize in Physics last year, to Alain Aspect, John Clauser, and Anton Zeilinger, where they used experiments with entangled photons, established the violation of Bell inequalities, and pioneered quantum information science using qubits instead of bits for information processing. So let's see how that story, how that story goes. And I think, I don't want to take too much of it. I think we'll get to the meat, and then you invite me another time. I tell you about my atoms. We have this proposal by John Clauser in 1969, proposing a concrete experiment, not using spin actually, but using light. But it's the same idea, using a pair of photons, not of electrons. Turns out it's easier in their setup. It's a pair of photons that are entangled, and instead of the spin, in spin of an electron, for photons, basically the same thing is called polarization. You know that light has two polarizations. That's why you can buy these wonderful glasses that when you drive don't give you a glare from the sky. So you can actually encode quantum information also in the polarization of light. Think about it as the spin of the photon. That's fine. So we can denote this as like this up-down arrow and the left-right arrow as the two states. Otherwise, it's the same thing. And a few years later, Clauser did the experiment. He took atoms that were creating a correlated pair of photons of opposite polarization. So one was up, the other one was left-right polarized. And now by measuring these photons far away from where they were created, namely here on the left and on the right side at the photomultiplier tube, playing with polarizers for each of these directions, he could test Bell's inequalities. I didn't derive Bell's inequalities, but here is a version of Bell's inequalities. They measure coincidence counts of these two photons under the various conditions of the polarizers. And you can imagine, like in quantum mechanics, if you rotate one polarizer to be vertical, and if you measure a click, then if you have rotated the second polarizer to be horizontal, you should also always get a click, because these two photons are created in this correlated fashion. And this graph shows that quantum mechanics is right. These are the data points. The line is the prediction by quantum mechanics. The agreement is beautiful, but of course, we have to ask, where do I see that classical mechanics is wrong? And that's where we have to look. For example, we can look at these very special points of the angle between the two polarizers at 22.5 and 67.5. I should take those two data points, take their difference. Okay. Subtract 1/4. And the result for classical theory should be smaller than 0. Okay. So these two values at 22.5, 67.5 should be closer together than 1/4. Now you have to squint your eyes to see the difference between this distance and 1/4. This is roughly 0.1. 1/4 higher up would be 0.35. Yes, that doesn't quite get you to that data point, and they give you the value, you don't have to read it off, they obtain a positive difference here, 0.05, in clear violation with the inequality, which would say this has to be smaller than 0. So again, I didn't derive the equation, but they test it and find a local classical theory which would predict this equation is violated. Quantum mechanics is right. Alain Aspect repeats the experiment with significantly better precision, but otherwise it's actually the same experiment. And then plugs a crucial loophole. Maybe there is some secret information transfer. As I measure on this first particle, maybe there's some secret classical piece of information that flew magically over to the second photon and told it to be aligned in the way we think is quantum mechanical. Well, I can fix that loophole by making the choice of the polarization alignment of the polarizers very quickly, randomly, at very high speed. At such high speed that there is no time in the world for a classical signal, which has to propagate at the speed of light, to travel from one photon, from one detector, if you want, to the second detector. And they do that experiment again, see quantum mechanics is right. Many experiments followed, all of them demonstrating, yes, quantum mechanics is right. We're not super surprised as practitioners of quantum mechanics, but pleased, that things are not simple and trivial. There is no local reality. We have to give up on this idea of the local reality. Particles can be entangled with each other over a distance, over a spooky distance. To finish maybe on the 3 Nobel Prizes, Anton Zeilinger realized an experiment, for example, among many other things, on quantum teleportation. I do worry it's a bit too much for you to now also take in, but basically there is a beautiful way to make use of these correlated pairs of photons to copy one quantum state from over here, maybe at Alice, to over here at Bob. That seems magical, but is not magical. I'm not doing any measurement on that first particle, so I don't gain any information while I do that transfer. I just do a very clever correlated measurement of the 2 particles. And it's not hard to understand. I just think probably by this time we have gone through 100 years of quantum mechanics, we might be saturated. So I think I should stop here, tell you what I wanted to talk about, namely strong correlations in ultra-cold gases, which is what I do. But I mean, I'm also happy to continue, but I don't want to take up too much of your time and just instead open it up for questions.
I have a question.
We have a question in the chat.
About correlation and entanglement. If you are, let's say, 2 worlds separated apart, and you measure the spin, let's say, of world 2, and so you immediately know what the spin of 1 is. Now, that information in world 2 will tell you what's going on in world 1, so you could prepare yourself, let's say, with developing weapons that will destroy world 1. And so that information is very useful, even though 1 doesn't know that that, but you can prepare yourself knowing what happens, could be millions of miles away. I mean,
Yep.
Star Trek, we're talking about Star Trek here.
Absolutely.
but what I'm saying is that information is very useful, and it's valuable. So how do you account for that?
It's absolutely right what you say. It is valuable. In fact, it is. You can base secure cryptography on this. And what you say is absolutely right. Like I now know something about. You said world one. We would have to say we should not distinguish two worlds. It is one world that contains both particles. That's I guess an important conceptual point. But it's true. Once I measured what particle 2 is, I have knowledge about what particle 1 is, and indeed, if I now sort of make particle 1 come back to me, to my experiment, and I measure it, I will with certainty find it 100% in the opposite spin state. So that's absolutely right, and it is extremely useful. It's very useful correlations. As I mentioned, it's stronger than classical, and so you can base quantum information, you can base quantum communication on that. You can decide to only communicate using correlated pairs of photons, for example. And if there was ever any eavesdropper that would try to intervene in between and do a little measurement of trying to catch your message, it would immediately destroy the message. It would garble the message, and I would immediately notice as the receiver that something terrible happened, because I just get like garbage, a garbled message back, and I know someone is eavesdropping. So it's extremely useful for quantum communication. It's extremely useful for quantum information, although maybe the proof is still ways out. There is the sincere hope that using entangled states of atoms for quantum information is going to be superior to doing information processing on your laptop and on any supercomputer that you can find. And in my lab, we have some experiments where I can already say what we do, what we measure, cannot be computed on even the largest supercomputer in the world, in principle already, because the particles in our experiments are so strongly correlated. So it's extremely useful, extremely powerful. We're still not at the stage where we can compute something in using the quantum computation aspect, like the zeros and ones, these superpositions, that something useful, say something useful that beats something that a supercomputer could do with qubits. I would claim we can already learn something that cannot be calculated on a supercomputer by doing measurements on many atoms in our experiments. But that's sort of the analog way of using the quantum nature of things. And yeah, it's very powerful. That is acknowledged. Everyone is behind that. This is actually very powerful.
Martin, we have 3 questions. Could you take a look in the chat? We have 3 questions for you.
So one is, okay, so because the two particles have the same and opposite spin orientation at time t1, and then the same at time t2 when separated, this is a type of memory of prior, more local entanglement. Yes, beautifully said. I prepare them at time t1 in such a state of opposite orientation. And as time goes on, that will not change unless someone or something has interfered. So if nothing has interfered in the meantime, even though now at time t2 they're widely separated, we still know that they are in this oppositely oriented spins. So yes, it's a type of memory. Very well said. It's very well said. It's a type of memory of prior, more local entanglement. That I couldn't say it better. Second, how do you create an entangled pair of photons or electrons? So, beautiful question. So sorry that it's absolutely zero time that I have to discuss it. Let me explain, for example, the correlated pairs of photons. There are many ways, but there are processes by which an atom, an excited atom, which is in an excited state, emits not just one photon, but it can be that it spits out two photons in rapid succession. And one can choose systems such that these two photons must have their polarizations orthogonal. So there are certain two photon processes in atoms that allow that precisely create for me this pair of photons that must have the polarizations orthogonal to each other. I don't know which photon has what polarization, but I do know they have opposite polarization. So it is nonlinear processes in atoms that give me that. I can have a simple example from my lab, which I'm sorry I didn't get to, where we actually take two atoms, and these two atoms are, we do know that they have opposite spin. And in the lowest temperature state, we cool them all the way down to the lowest state that they can exist. We absolutely know that they have to be in this state where if one is spin up, the other must be spin down and vice versa. So how is that? How is that possible? That would need for me to explain what fermions are. Let me give another simple example. It's a bit more a Gedanken experiment, but very simple. Take the helium atom. There are two electrons in the lowest shell, only two. And these two electrons must have their spin opposite to each other. All right. If they have the same spin, that's the thing I couldn't tell you about. They don't want to be together. They are fermions. They cannot share one and the same quantum state. So if they want to be in the lowest shell of the helium atom, which they want to because the Coulomb energy is the lowest there, it's like most profiting from the attraction of the nucleus, then they have to make sure that their spins are anti-aligned. And now you can imagine doubly ionizing that helium atom and having these electrons fly away from the helium atom. You now end up with two correlated electrons, one and the other, which you know they must have opposite spin. So this is a bit of a Gedanken experiment, but it actually happens in experiments. We can actually create things like that. What you can always use is, like in this example, interactions, attractive interactions between atoms. Then they like to be in one and not the other spin configuration. And now, once you have made them interact, now they can leave again, and you can measure them.
Zeilinger used a down converter to produce correlated photons.
Yes, so that's in a nonlinear crystal. It's basically the same thing as I mentioned for atoms. It's the same thing because it's now in a crystal, so it's a whole collection of atoms. It's a two photon process in that crystal, where where spontaneously you get actually two photons that rain down with opposite polarization. So it turns out, depending on the polarization, the photons fly out in slightly different angular patterns, but there is one location where these two patterns overlap, where you no longer know, is this a horizontal or a vertically polarized photon? And that's what they used. Here is more question, a rather broad question. Are you satisfied with the conventional definition of information as valid in the context of entanglement across distances? Is there any reason to see information differently? I don't think I have a good answer. Am I satisfied?
We think of it like Einstein.
Huh?
We think of information like Einstein.
I think, is there any reason to see information differently? I wonder what is meant. Like, yes, differently from classical information, I would say yes, we have the proof that we need to see information differently from classical information. But the question already seems to accept entanglement across distances. So
This is Mark Edelman. I'm just, what I meant to ask is, how do you know things, such as how do you know that two distant particles have remained entangled? So it's the question of how to know something.
yeah, it's a beautiful question. In fact, you don't know it from one measurement. You would have to repeat the same measurement over and over again and accumulate statistics, accumulate information on the correlation between the measurement outcomes. So this would have to be, there are two experimenters in two rooms that are distant from each other. They share these, we call them bell pairs, and they make these measurements and later come together, maybe they pick up the phone and communicate to each other the outcomes of the measurements. So then they can write down the Bell's inequality, basically they can arrange these data that they figured out in such a way that it would show, if they were entangled, these atoms, a violation of Bell's inequality. So they can actually do this Bell test. And if the classical theory is violated, they know that there is a degree of entanglement in these atoms or photons that they shared. So how does one know? Well, precisely by doing this Bell measurement. You need some sort of...
Okay, that speaks directly to my question. Does this mean that in the context of entanglement, information becomes something statistical rather than something with discrete states? This is what puzzles me.
I see the good. I'm trying to wrap it around, and the answer is number one, yes. So we have to. We can only ever have a statistical understanding of what happens. If we are to do some sort of quantum computation, we cannot do with a single measurement. We always have to repeat over and over again, like in the double slit experiment I showed. We have to repeat, and only over many repetitions of the experiment, if it's performed in an identical way, do I start to see the interference fringes, which reveal the quantum mechanical nature of things. So I would say yes, we have to repeat, and acquire statistics.
Can I ask a question from here?
Thank you.
For a long time.
Ted, can you hear me? Good. Do you want to go ahead and ask your question, please?
Yeah, okay. So almost 40 years ago, my brother was doing his work as a graduate student with Professor Graytack with spin polarized hydrogen. And he cooled hydrogen in a purely magnetic trap, and with cooling up, pre-cooling with a dilution refrigerator. No laser cooling was involved. And so they had a sort of a classical collection of spin polarized hydrogen atoms in this trap. And then when the magnetic field was turned off, he measured the evaporative cooling that went on as the more energetic particles escaped over the barrier. But he didn't think about this, an EPR thing, because at the time nobody was really looking in that direction. So the question is, would that have been basically a entangled hydrogen, spin polarized hydrogen, then essentially until the collisions started occurring with the walls and other things to destabilize the system?
That's such a beautiful question that would immediately lead me into the second part, because I am Dan's great grandchild, scientifically speaking, and I was about to go and discuss precisely Bose-Einstein condensation and trapping in magnetic traps, and describing how you can actually get to such a state where you have many atoms sharing one and the same wave function. I flash here one slide where the method of cooling to this ground state is depicted, which was first demonstrated in Dan's group, Tom Graytech.
Well, it's clear we have to have you come back.
And I would love to give you that story. And then I could tell you about Wolfgang Ketterle's measurements, taking two Bose-Einstein condensates, which are now two waves of matter, and observing quantum mechanical interference between them. So indeed, if I detect a single atom out of that soup, I had not yet learned much about what's going on. But as I detect more and more of these atoms, which in these experiments happens in one shot because we can just take pictures of these things, I start to see the interference fringe between the two condensates, and see therefore the correlations between these atoms. So it's a beautiful state.
Yeah, I think my brother should be on that list of names and faces there, because of the work that they did. Published in Physical Review in 1986.
Wonderful.
Excuse me a second, Martin. It is close to the end of our time. Actually, it is the end of our time, and I see several more questions in the chat. Could you take a look at those and see if you can spend a few minutes answering any of those?
We have one question in the community center, please. Can we ask that?
Sure.
Yeah, I actually have two questions that perhaps are entangled. The first one is, can we consider entanglement as a property of a given, let's say, electron, photon, anything, or a state? In other words, we think of mass, we think of charge, we think of polarization as properties. Should we now also think of entanglement?
I love the question. And
second question is, when does entanglement occur?
Right. So I love the question because it allows me to point out again that the entanglement is a property that is shared between at least two entities, not a single one. Like if I just do a measurement of a single atom and I have nothing to correlate it with, I will not see whether or not it was in some beautiful entangled state with some other atom. I will not be able to do that. I always have to correlate measurements on one and the other atom to reveal quantum entanglement. So it's a shared property, it's a shared resource, and not something attached to a single entity. So that's a wonderful and important point.
Second question is, when does it occur?
When does it occur? So when particles interact with each other, more often than not, if that happens in a very pristine situation, they actually do entangle each other. Like if a particle scatters with another one, it actually now has become correlated, entangled with the other particle. And the wave function of the combined system might, in most cases actually, I would say, have this property of entanglement. It's just so fragile that if it now scatters yet a third one, it will very quickly scramble this beautiful correlation, and I will not see it easily. So it requires sophisticated experiments to see entanglement. But when two particles meet and interact, they entangle.
Thank you.
I love the one comment that you would love me to talk about. I would be so happy to come back. That would be fantastic. And then in the other one is also just a comment that in frequency doubling you get correlated photons. So yes, absolutely. Then is it possible to disentangle two particles entangled close together in space-time? Then is it possible to entangle two particles at a distance? Then can these particles be disentangled? That beautiful question. So the first one, can I disentangle two particles entangled close together in time and space? Yes. Yes, I can actually turn a state of entangled atoms that are close together and manipulate the two atoms, for example, by playing with the interaction strength between them, and disentangle them, bringing them back into a state, for example, of up and up. That would be an unentangled state. Now both are up, but there's, they do their separate thing. It's not correlated. Each of them is up. I can do that. So the answer is absolutely yes. I can disentangle when they're together in space and time. Opposite question, is it possible to entangle two particles at a distance? The answer is yes. Yes, you need some way of having a long-range communication between these two. So that can very well be non-local interactions. Maybe the Coulomb interaction is a very dramatic example. But dipolar interactions are also fairly long range, decay a little faster. And those can be used to entangle two atoms that are separate from each other. Absolutely. And that is happening in experiments right now, in experiments on atoms in traps, where they are separate by several microns, but they're easily entangled thanks to strong dipole-dipole interactions between the atoms. So the second answer is also yes. Then can these particles be disentangled? And the answer is again, yes. I can also disentangle these particles even if they're at a distance, again, by using something like long-range interactions. Beautiful question, I will say.
Doesn't just measuring it disentangle?
Beautiful. Okay, cool. Yes, if I measure it, I know one is spin down, the other is spin up. And that's it. From now on, it's just they are tagged, so to speak. They're no longer correlated. Now I already know what one guy does, and yeah. So that's after the measurement. You also know exactly this particle is down, this particle is up. So there's again, it's purely classical information at that point. Yes. Can multiple photons?
Can multiple photons, electrons be entangled to each other?
These are such fantastic questions. Yes.
Everybody did their homework.
This is super cool because I only talked about 2 because that's already crazy. But you can do it with 10 or 100 or dare to think about 500 and 1,000. Yes. So in fact, people strongly believe that quantum information becomes more and more robust, actually, if you do clever setups where you entangle not 2, but more, like 10 or 20 atoms in what's called sort of a cluster state. Some aspects of these states can also be more fragile. Say you have a crazy superposition of 10 atoms down, but 1 atom up. You just don't know which atom is up. So that you would write as a crazy superposition of 10 possible states where the first atom is up, the second atom is up, the third atom, I don't know which one is up. Yeah, and that's a highly entangled state. But the moment you measure the information on one of the atoms, you're actually up. it destroys the state. So one has to be a bit sophisticated to figure out what are robust states and what are states that are very fragile. And people now working on these quantum computers are precisely going that way. They're trying to take not 2, but 5 or 10 qubits to define a single logical qubit that is more robust than each individual ones. And it appears there was a very recent paper by the Google group in Nature that they have shown going from 3 to 5 qubits actually made their logical qubit more robust than the individual ones. So there's absolutely a hope to actually get very robust qubits by making many particles entangled with each other.
The last question from Mark. Do you want to state it yourself, Mark? Maybe not. Can you read it, Martin?
Yeah. So the next question will be, can you have multiple different types of entanglement of the same particles? Yes, you can. Beautiful question. And can just one disentanglement occur then? Yes, absolutely. So we very naturally in our experiments that at some future point I might actually tell you about, we know, for example, we have a entangled spin state. So we know spin up, spin down is entangled, but we can also entangle the motional states of these atoms, which is a separate story. Completely, these are separate worlds. And of course, even crazier, I can even then start to entangle these two worlds, the spin and the motion of the particles. So to go to an even crazier state of these two atoms. So that's precisely what we can do. That's what I would have told you about, that we can actually make motional superpositions of two pendula, if you want, two atoms coupled together to give us a quantum pendulum qubit. So that would be what maybe is in stock for you if you ever have me back. I don't know.
Tony has one question here, but I want to be respectful of your time. You can.
I'm fine. I'm good. No pressure.
Can you see Tony's question?
Yes. If you measure the properties of particle 1 in world 1, how do you know where world 2 is? You don't, right? You don't. You don't know where the second particle is. And you also don't know by just measuring the properties of this first particle that it was entangled with anything else. You don't know. That's funny, right? You need to actually correlate your measurement outcome with what someone measures with the second partner in this two-particle entangled state in world 2. They have to compare notes, if you want, correlate their measurements and realize, whoa, this is something I cannot describe by just a classical local probabilistic theory.
Good place to end.
I think that's a good place to get. Barry, do you have a quick question?
He's muted. You're muted, Barry.
You're muted.
Sorry. If you have two photons that are equal and opposite, they're at phase lock synchrony going in opposite directions. If you have two receivers that are at arbitrary distances, then when the phase of one arrives at the receiver on this end, it's not guaranteed to be in the same phase as the other. So you might have a strong E field on one detector and a zero E field on the other. What happens if you go back to Bell's inequality and you derive it where the directions are fine of the E field, but the amplitudes are arbitrarily uncorrelated?
Beautiful. That's actually that can what you describe is a beautiful trap in some ways, a trap of our understanding. Because what you describe about the phase of the light field is the wave-like nature of the light. But when the detectors make click, that describes the particle nature of the light. It makes click. There is one photon somewhere and not zero. It depends on how you set up your measurement. whether you will be sensitive to the phase of your light field, or I should say the phase difference between the two light fields,
Right.
Like in an interferometer setup, or whether you basically know nothing about the phase, but you know the number of photons that you have. There is a beautiful uncertainty between phase and number. So if you say, I have particle detectors and they measure click, 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 particle number, I wash out phase completely, and vice versa. So it's a beautiful, subtle point that just like position and momentum do not commute. They're not sort of good pairs of experiments to do. You can either know one or the other. The same is true for particle number, photon number, and the phase of the light field. They are also complementary. So that has to be taken into account when analyzing the experiment, as you mentioned. And there is a formalism that runs through beautifully that can always give the right answer. So it's totally, you can make all the predictions come out right, but there is this subtlety that one will notice between phase and number measurements of light. I hope that sort of helps. It's not maybe a perfect answer to your setup, but
Well, see, I was trying to figure out, Feynman says, if you make a prediction and it doesn't agree with observation, then the theory that makes the prediction is wrong. That's as simple as it is, says
Good.
Feynman. And so my question is, what was wrong with Bell's assumption? And the thing that comes to mind is, I think he assumed that things stay in phase, which they don't.
yeah. And maybe first I have to say, I doubt that Bell doubted quantum mechanics. I think Bell embraced quantum mechanics and just was so happy to derive a way to prove it in an experiment. But I guess that's agreed. So the assumption that he makes to derive his equation is that of a local reality, that the orientation of my Stern-Gerlach magnet in experiment A on the left side does not change the outcome of the experiment with Stern-Gerlach magnet B in the other room, which is super reasonable. Like, makes complete sense. Yeah, that these should be completely uncorrelated,
Right.
and it should only depend locally on what happens. And that is just not right. That is just not right. One has to think about this non-local pair always being correlated. So that was the thing that was assumed, a local classical statistical theory. If you allow for non-local classical probabilistic theory, then his way of reasoning would not get a contradiction with quantum mechanics. But of course, that's precisely what Einstein absolutely didn't want to have, coming up with a non-local theory. That would be like, he would have hated a non-local classical theory.
But under Einstein, we know that timekeeping is local. Timekeeping here isn't the same as timekeeping there. So if I assume that time ticks at the same rate everywhere and every when, I think I can do Bell's derivation. If I assume that time ticks at a local rate, depending on the local gravitational field, then I don't think I can do Bell's derivation. I think I have to do a gravitational path integral, which I don't think Bell did.
No, gravity was not involved.
I think if, Einstein died a decade before Bell wrote his paper. I think if Bell was still alive, he would say, you're assuming that time ticks at the same rate and that space-time is a Cartesian regular grid. It ain't. Space-time is warped and timekeeping is local.
I think there is an issue here that if you say I measure something very local in time, and at time things, right, that you could catch the wave in one experiment at the peak and at the other experiment at the what is the word, trough?
At the minimum.
The minimum. Thank you. It's fantastic, right? But then you're talking about the wave-like nature of the light, but then you don't get the click.
Right.
you don't you
So
don't
now make a new prediction. Now make a new prediction where you don't assume that they're at the identical phase at the two detectors. I think you get a different, I think you get a different inequality.
Yeah, let me state that what I would now have to do is I would have to take it to a piece of paper
Right.
and draw a Michelson interferometer versus just a beam splitter.
Yeah.
And I think I could explain to you that the differences. If I have a beam splitter and I have a single photon that hits that beam splitter, I will always get, a click in one port or the other port. The photon goes one way or the other. I might not know which way a priori, but at least I will always get a click. So very particle-like. If I do a Michelson interferometer and then put my detectors at the output of the second beam splitter, I will now find a beautiful correlated outcome of the measurements in each detector, which actually tell me about the phase difference
Right.
that the light has acquired going one or the other path of the Michelson interferometer, even for a single photon, which is amazing. It's beautiful.
Right.
And that experiment therefore measures the wave-like nature of light. The beam splitter with a click is very, very much particle-like. So it depends on the experimental setup, whether you measure this phase you're talking about or you measure the number. And I don't think we would get a new derivation of Bell's inequality. But however, I think the idea of putting gravity into the mix is beautiful, because that's the last thing that we absolutely don't understand how to put together with quantum mechanics, gravity.
Bingo.
And something like an entanglement between particles at different heights or something, could be a beautiful way. At the moment, I don't see a new physics come out. I think at the moment, I would be able to describe it by just like the different energies in the gravitational field of one particle and the other, and I would perfectly be happy with the standard quantum mechanical formalism. But maybe someone comes up with a clever experiment or clever thought experiment along those lines too.
Thank you so much for a wonderfully interesting and informative presentation. It was just tremendous.
Thank you so much for having me.